Welcome to Khetztutorials, and in this video I will be talking about limits. So this is the first video under differential calculus, and yeah, let's get right into it. So the notation is basically something like this, and the idea is that we're basically asking, so let me first state what this means or what we are talking about when we talk about limits, right? So we're trying to approximate the value of a function as one variable inside that function basically goes to a certain value. So what does that actually mean? Okay, so I'll try to explain this in 2, if not 3 ways. And the first way would be a question. So the question is, what happens to this function when we take this value, when we take the variable x to a, or when x goes towards a? And in a graphical sense, we basically know that if we have a continuous function, so we have a continuous function, it would be something like this, or a parabola, or a straight line, whatever. Now with these kind of functions, we can draw a line, or we can follow along, and actually, if we have a car or something like that, you can basically drive all the way up, down, until infinity, or whenever. If you have this case as well, you'd have some sort of car, it can travel over here. But what if we have a point, or what if we have a break over there? We aren't really sure what goes on over here, right? And we have that same car situation. So let's see. So let's say we have some sort of ramp over there, and we want to travel, but at this point we have some sort of discontinuity, or we don't know what actually happens at this point. Well, you basically would not suggest someone to travel using this road, but you'd try to quantify, or you try to measure the safety, or how safe it would be. Let's say it's the only route that you have and you're trying to actually use it. So we are trying to approximate what happens at a certain point in a function where we have a discontinuity, or where we aren't quite sure of the behavior of the function. So in terms of a question, what happens to f of x when x approaches a? And we can, as I said, we can talk about this graphically, and I'll do that in a bit, but we can also actually find a value which is an approximation of what happens at that point. So we can say that such a function at a certain point is not exactly fully defined, and we're trying to approximate the value of that function at that point. So that is a lot which I just said. So let's move on to some examples and actually talk about everything that we can possibly talk about, I guess. So now let's say that we have this. You basically read this as saying the limit of f of x, so limit of f of x as x tends to a. And a can be anything, can be infinity, can be 0, and we can talk about it coming from the left or from the right. So the approximations can actually differ depending on whether you're looking at the graph from the left or from the right. But at this level, we don't really talk about stuff like that. We just approximate it based on whatever function that we have in front of us. So we're talking about the limit of f of x as x tends to a. Now, before we talk about examples, another thing that I want to mention is that if you have f of whatever this is, then we basically substitute that thing wherever we see, let's say it's a function of x, and we have x squared plus 4x. Whatever we put here needs to be substituted in the place of x. So for example, if you have x plus 4, you basically substitute that wherever you see your x, or where x was in the previous case. So now this is the new equation, or this is the new expression that you'd have if you were to turn to something like this. So wherever you see x, you basically substitute it like that. Don't reason much when you find stuff like this. You just basically substitute whatever you have here in the place of whatever variable that you're dealing with. Usually it's x. It's not always the case though. So for example, if you have x plus h, then wherever there was x, so in the place of x or whatever variable you have, you just basically substitute this x plus h. That is just another thing that I wanted to mention before we move on to the actual examples and some actual explanations and solutions to limit problems. So now let's start with the simple problem. One other thing is that we are trying to avoid division by 0. And we can do this by basically factorizing or factoring out. This is a method that you can use to avoid dividing by 0. So if you have some expression at the top and expression at the bottom, if you can factor out something here that is going to cancel out at the bottom to avoid division by 0, then that is basically what you do. And then you'd basically do substitution for the rest of the problem. So this is what I mean by substitution. If we have the limit of x plus 4 as x approaches 4, there is no danger of dividing by 0 in this case, so let's not worry about factoring out or factorization and stuff like that. What we can do in this case is direct substitution, right, to find the approximate value of this expression when x approaches that value. So we can simply do that just by substituting this value in the place of the variable in question. The variable in question is x, right? So we're just going to substitute 4 in the place of that, and our answer should be 8. But now let's look at another example before we move on to a graphical example. Now let's talk about something like this. This is -1, so let me just write this using a different color, just so it's a bit more visible. This is -1. X, that's x squared. My handwriting, it's kind of funny, but okay. So that's what we have over there. And yeah, so now we want to find the limit of this expression as x approaches -1. So now if you were to do the direct substitution like in the previous case, if you were to substitute -1 over there, you'd have a denominator of 0. And if you remember, we are trying to actually avoid such a thing, right? Because we basically try to approximate the answer to this with something like infinity or negative infinity, which is not quite appropriate for this level, or which is not the answer which we're looking for, if I can put it like that. So now what you do is you basically factorize the top, and doing so, if we factorize the top, we expect to have this at the top. And if you look at one of the factors at the top, they can cancel out with the factor at the bottom, right? And what you'd finally have is this. So now this original question now became the limit of x minus 5 as -1 as x approaches -1. So now we can now do that direct substitution, and it would lead us to -6 as our answer. So this is how you'd, in a nutshell, this is how you basically answer your limit questions. Try to avoid division by 0, factor out wherever you can, and then do your direct substitution. Now, to further understand what is actually going on here, we are going to do a sketch. So let's sketch something. So let's sketch these two graphs. So the first one would be g of x equals to x plus 4. And the other one would be f of x equals to x squared minus 16 divided by x minus 4. So let's try to sketch these two things. Now, If you look at this, it doesn't exactly take on a particular form, so you can't exactly tell what kind of function it is. So a method, or one good way or one easy way, would be to try and simplify this thing to something that we can identify as one of the functions or one of the common functions that we actually do know. And if you do that, at the top we have difference of squares, which will just be this, and at the bottom we just have x minus 4, and this will cancel with that, which means this function, in a way, it actually is the same as that one, but we can't sketch them in the exact same way, and here is why. So the first one, we basically see that it's just a straight line. It's a linear function. It's just mx plus c. So we have a gradient of 1, so y equals to x should be somewhere there. But now if we add, or if we shift y equals to x by 4 units up, then expect our graph to fall somewhere there. It's a positive function, and that is why it is increasing in that fashion, right? And you can once again look at my series on functions if you want to revise on this. So at that point, it should cut at 4, and here it should cut at minus 4. So this is our g of x, right? So that is perfectly fine. And this is defined everywhere. If we were to talk about the domain of this function, it's basically defined everywhere, right? But now, if we were to look at this function, the final formula is exactly the same. If you look at it, the final formula is exactly the same, and we're just about to draw the same thing, but it's essentially wrong if we look at the original thing, because at x equals to 4, which is some point over there, we will have division by 0, which is what we're trying to avoid, and we don't quite want that. So at this point, there is a discontinuity, and we indicate that by this circular thing on your graph, and that shows that at this point we don't necessarily have a definite value, or we don't quite know what is happening there when we have division by 0. Even if you put that into your calculator, you should get a math error or whatever your calculator is set to say, and that is because we don't know what happens when we divide by 0. So that is shown by this circular thing over there. So the function is exactly the same, but the domain of it is basically everywhere, or all the x values except 4. Because at 4, you should get division by 0, which is what we're trying to avoid. So look out for this. When you simplify functions and they take on a certain form, make sure that you enforce this restriction so that you don't have that division by 0. So I hope this was a good overview of limits and how you basically work with limits, how you sketch this stuff, how you analyze, and how you solve using direct substitution. And if you haven't subscribed, please subscribe. If you like this video, just give it a thumbs up, and I will see you in the next video.